About nonlinear inequalities, something that stands out to me is the word inequality. I know that's going to mean less than, greater than, less than or equal to, greater than or equal to. And if you think about like solving or graphing inequalities, it usually is the case that there are lots of answers, right? So your answer may be another inequality. There may be some shading if you're thinking about it visually. So there's not like a single answer. And then the fact that it says nonlinear just means these aren't lines anymore. So think about in chapter 2, we've covered two nonlinear type of functions, polynomial and rational. So we're basically doing polynomial inequalities and rational inequalities. Now, we're going to start by looking at this with your groups as a visual problem. And then what we're actually doing in the textbook is the algebraic work for solving the inequalities. So we're going to look at the graphs now, but when we do the work, it's without a graph. Okay, so we're trying to make sense of what is it we're actually working with. So I've got a few graphs up here on the screen. These are polynomials, A, B, and C. And I want you to talk about with your groups the answers to these questions at the bottom of the screen. So first off, my whole goal here is, can you answer the question for this inequality? When is f of x greater than 0? And your answers that you give me, because there are lots of answers, it should be an interval notation. So you want to be thinking about interval notation. Now, in order to be able to answer this question, when is f of x greater than 0, you and your group may have to first talk about the sub-questions. What does f of x greater than 0 even mean? And what does f of x greater than 0 look like on these graphs? Once you decide the answers to those two questions, you should be able to come up with the intervals. And then lastly, after you do the interval notation for those, think about what numbers are showing up in the interval notation. Those are what we're going to call critical values in our notes. So what are the critical values when you're doing polynomials? What are the important numbers to look at? So go ahead and have conversations with your groups. Remember, you're trying to get intervals for your answers to A, B, and C.
So wouldn't it be parentheses 0 and 2?
And then B, negative 3 parentheses to 0 parentheses, and then another thing, 0 to infinity. And then for C, it's never greater than never greater than 0.
Negative 3 to 0. And C would be it's just like right there. So we don't have to put anything down on it.
Okay, let's come together and see what we got. First of all, I'm going to ask these two questions. What does f of x greater than 0 mean? Y is positive. Y is greater than 0. What does that look like on a graph? It's above the x-axis. So you could probably go through and you could look at different sections of the graph. In order for y to be positive or y to be greater than 0, then your points have to be above the x-axis. In part C, there is none, right? So you could put NA or null set, whatever you'd like. If we were to write this in interval notation, like for part A, this part that I have highlighted here, what numbers did you use in the interval? Negative 3 and negative 1. And did you choose brackets or parentheses?
Parentheses.
Anybody want to argue for parentheses or for brackets?
Are you for parentheses?
No, now that I look at it.
Oh, we've convinced
Because
Kenzie
negative-
without even telling
Yeah.
her.
Well, because
This is a sign of
negative
true
one-
intellect.
Like it's 0, yeah.
Yeah.
I didn't realize that.
Okay, so if you were -3, then you are 0. So you guys are arguing now. It should be parentheses. Sorry, Tom. No fight for you today. Okay. And then if we did part B, notice if it's a polynomial and it's turning multiple times, it could be more than one interval, right? So we would name one interval -3 to 0, and then if you want to do union, the other interval would be 2 to infinity. That's when y is greater than 0. So what were these numbers in the interval? -3, -1, -3, 0, 2. How are they special to the polynomial? They are what? X-intercepts or zeros, right? We spent section 2.3 and 2.5 trying to find x-intercepts and zeros of a polynomial. So now we know if we're trying to solve polynomial inequalities, the x-intercepts are really important numbers because those are the places where you're allowed to change signs. Okay. Now, notice, depending on the multiplicity of the 0, you may or may not change signs. So here, -3 and 1 have an odd multiplicity because they're actually crossing the axis. So if you have odd multiplicity, you'll go from negative to positive and positive to negative. Okay, same thing in B. Everything that appears to have an odd multiplicity because it's crossing the axis, and it will actually change signs. In part C, this 0 of 3 must have even multiplicity because it's turning on the axis. So we're increasing, we come up to 0, but then we turn around and we're still negative. So it's negative, negative. So you may or may not change signs as you get to a 0, but that's where you potentially could change signs. Okay? So now we're going to put this into words, into description. What are we going to do algebraically if we don't have a graph to solve the polynomial inequality? And I'm going to say solving nonlinear inequalities. There's a few parts in here where I say leave a little bit of space. We're going to add something for rational functions. So, solving an inequality is really like solving an equation. And in order to solve an equation, you would want one side to be equal to 0. So the same is true here. Set one side of your inequality equal to 0. Step 2. Find your critical values. And what did you say critical values were going to be for us in a polynomial? X-intercepts. So we're going to have two lines here, one for polynomial and one for rational. For polynomial, you can say x-intercepts. Okay, we'll fill in the rational later. Okay, we'll look at those graphs in a little bit. And think about in the previous parts of the chapter how we were able to find the x-intercepts of polynomials. There's really two methods that we've talked about. One method is you could factor the polynomial. That's easy. The other method is if you count and factor a polynomial, you can make a list using the rational zero test. You could narrow that down with Descartes' rule of signs. You use synthetic guess and check, looking for smiley faces, zero remainders. Once you find some zeros, you might be able to find some others. That's a lot of work, right? Which one do you suppose is going to happen if we're doing solving polynomial inequalities? The easy one or the hard one? Easy one, yes. So make a little note to yourself. You should be able to factor these to find x-intercepts. Certainly I could give you a problem where it was not factorable and you'd have to find the zeros some other way, but that would take up way too much time. So we're not doing that. All right, step 3. After you find the critical values, this is where you start testing the intervals. So in a polynomial, when we find the critical values, the x-intercepts, we know that those are places where the function equals 0. We want to know about the value of the function in between the zeros to see if it's positive or negative. So I'll show you how I can test the intervals. Now I'm going to need some help from the people. Oh, never mind, I did it. I'm getting really good at it. Never mind. There's two spots right here. I have two things that I'm going to tell you or warn you to be really careful about when we get to rational functions. So if you want to leave a little bit of space after step 3, I'm going to put that in there for rational functions. And then step 4 is how to write your answer. So your answer, you're going to have two parts to your answer for me. One is going to be the interval notation. And you'll think about parentheses or brackets. Does it equal 0 or not equal 0? That type of stuff. And then the other part is a number line graph. Instead of using open circles and closed circles, I just draw like the parenthesis and the bracket. Okay, so you'll see my example. And then that way you don't have to do like too much extra thinking there on drawing the number line. You just kind of put in your interval notation. Okay, so we're going to look at an example with a polynomial, and then after the polynomial, we'll look at rationals, see if they're the same or maybe different. Okay. So here's our polynomial. X cubed minus 3x squared minus x is greater than negative 3. So you're looking at this problem like later on in another class, wherever. You notice it's an inequality because it's got the greater than sign, and it's nonlinear. It's a polynomial because it's cubic. So you know in order to solve the polynomial, you need one side to equal 0. Okay, so we're going to add that 3 to the other side. And this is great because now it's set up for greater than 0, which I can think about y being 0 is the x-axis. To be greater than 0 is the part where it's above the x-axis, right? So now it makes sense. And then we've got to factor this. So since it has 4 terms, we're going to use factor by grouping. So out of the first 2 terms, you can take out x squared. What can you take out of the last 2 terms? Negative x plus 3? Negative 1. Remember, you always have to take out some number, positive 1, negative 1 at the very least. So then we're left with x minus 3. We had just reviewed factor by grouping when we were doing slant asymptotes. So these things have to match. If they don't match, it's not factorable. So x minus 3 is a factor, and then your other factor is made up of these 2 things that you factored out. So x squared minus 1. Now, you may be able to find the critical values right now. Set those equal to 0 and solve. I notice that x squared minus 1 is a difference of perfect squares. So I'm going to completely factor that. I'm going to write this as x minus 3 times x minus 1 and x plus 1. And the reason why I like to have it completely factored is I'm going to show you when I'm testing my intervals. I think it makes for like a quicker or an easier way to check the signs. And I'll show that to you in a little bit. But now we know our critical values. So our critical values or our x-intercepts are 3, 1, and negative 1. The zeros to those factors. Okay, so the next part of this is a number line where I'm going to like work stuff out and try to figure out what's happening with my graph without graphing it. Negative 1, 1, 3. Okay, each of those points on the number line represents an x-intercept. What is the function's value at the x-intercepts? 0. So this is equal to 0, this is equal to 0, and this is equal to 0. Since the whole question that we're trying to answer is when is the function greater than 0, those x-intercepts should not be included in our answer, right? We will want to use parentheses. Now, what I have to do is figure out what's happening in these 4 different sections of my graph. So one way to do this is to just test numbers. So if I start over here on the far left, I want to test something that's less than -1. What could I test? -2. And here's why I like to have my stuff completely factored. I don't really care what the number is. I just want to know what the sign is. So -2 minus 3 is negative. -2 minus 1 is negative. And -2 plus 1 is negative. So a negative times a negative times a negative is still negative. So I really don't care what that number actually is. That just makes it easier. I'm not doing the math. I'm just figuring the signs. For the next interval between -1 and 1, you might test 0, right? That's an obvious choice. Now, I could go back and do my zeros like I did in my factors. But 0 is also a nice one. If I go back to the original polynomial at the top, if I plug in 0 for all the x's, what's left over? 3, the constant. So the y-intercept is 3, so I know that in this section it must all be positive. Between 1 and 3, I'm going to test 2. And so I'm going to go back to my factors. 2 minus 3 is negative. 2 minus 1 is positive. And 2 plus 1 is
Positive.
positive. So that's negative times positive, which is negative. Now, some of you may also be thinking about things like multiplicities. So remember we had talked about like multiplicity. Does your graph cross the axis and change signs, or does it turn and keep its sign? When we said the critical values were 3, 1, and -1, they all had multiplicity of 1. So that's odd multiplicity. So if we had tested this first section as negative, then -1 has odd multiplicity. We're crossing the axis at -1, and we're going to move into the positive section. And then we're going to cross the axis again at 1 and move negative. So we could expect this last group to be positive because it also has odd multiplicity, so it has to cross the axis. If I wasn't comfortable with multiplicities and making sure I had it right, then I would test a number, right? Now, one thing I like to do on the left and the right is test extremes. So I'm going to test 100. And when I look at my factors, that's so easy, I barely have to think. Positive, positive, positive. So if you can get away with a really big number, that just makes it super easy to tell the sign. Okay, so now we actually have to answer the question. Bless you. Okay, so remember, the answer to the question is, when is it greater than 0? We're looking for sections that are positive. And we had said before, at these values, it's equal to 0, so we don't want to include them. It's pretty easy then to give your intervals, right? From -1 to 1. And from 3 to infinity. You have 2 intervals of positive values. To do the answer on a number line, I just make a nice new clean line because that one's all crazy with my testing and stuff. And then this is how I graph it. Instead of open and closed circles, I just say -1 to 1. Shade in between. 3 to infinity. Shade to the right. And I have interval notation answer and a graph number line. Okay, questions, concerns on polynomial inequalities? Yeah, Chloe.
Like the open close circles make more sense.
You could do open close, yeah. I would not take off for that. Anything else? Just be careful, make sure I can tell what's open. Like if you're doing it on the number line, that gets tricky sometimes. Okay, now we got to talk about rationals. Okay, so I have 2 graphs this time. and I'm changing up my inequality. Instead of greater than 0, I have greater than or equal to 0. So I've got graph A and graph B. You want to think about when is the graph greater than or equal to 0. Think about that in interval notation. And most importantly here, what are the critical values in a rational function? Where is my graph allowed to change its sign? So go ahead and have that conversation.
Negative 1 is negative 2.
Yeah.
Oh yeah, you can go left to right.
And then you do the union thing, and then
For negative infinity,
parentheses
bracket.
to infinity.
And then it would be
Critical values are negative 1 and 2.
I don't know what trick is, but the one where it's like A on top right. I think it's negative 2. Or no, 2 because 2 to infinity.
And then
They'd be parentheses because yeah, and then touch.
Okay, I highlighted the sections where f of x is greater than or equal to 0. Okay, so same idea, right? It's above the x-axis, or in this case, it's equal to the x-axis. It's on the x-axis. If you were listing these green in interval notation, this one would look something like negative infinity to negative 1. This time you would include negative 1 because that's an x-intercept, so it's equal to 0, so you'd use a bracket. The next time that it turns positive is after the vertical asymptote, but at negative 2, is it equal to 0? No, it's not equal to anything, right? There's a vertical asymptote there. The function is undefined. So in this case, you would use a parentheses. Oops, sorry, that's positive 2. Okay, so you'd use a parentheses at positive 2 towards infinity. Okay. And some similar things happen over here. I've got a vertical asymptote to an x-intercept. So it's going to be parentheses negative 1 to 0 with a bracket. It can include 0 because it is equal to 0, but it can't be negative 1 because the function is undefined. And then after the next vertical asymptote at 5, all the way to positive infinity appears it's going to be positive. So what would you tell me are the critical values in a rational function? X-intercepts and vertical asymptotes. So let's add that to our notes up at the top. The potential locations for me to switch my sign are x-intercepts and vertical asymptotes. So I have here rational, x-intercepts, and vertical asymptote. If you need to make a little note to yourself from section 2.6, if you want to find the x-intercept, set your numerator equal to 0, n of x. If you want to find the vertical asymptote, set your denominator equal to 0, d of x. And then my 2 reminders or things to be careful about there in part 3 are when you're testing and then trying to answer the question, be really careful about a vertical asymptote versus a 0. So zeros or x-intercepts, you could equal 0. So if you have an or equals to sign on your inequality, you're going to include that number. You're going to use a bracket. If you don't have or equals to, use a parenthesis. However, if it's a vertical asymptote as a critical point, then it absolutely needs to be a parenthesis. There is no graph at the vertical asymptote, so you should not have a bracket there. So always exclude the VA. Always use parentheses. Other than that, everything else about the steps or the process is the same, right? Get it equal to 0 so we can compare it to the x-axis and then answer the questions as necessary. So here's our example for a rational function. 3x minus 5 over x minus 3. And we want to know when it's less than or equal to 1. And first things first, we want to make it in line with the x-axis, so we want to make one side equal to 0. So we're going to subtract that 1. So that gives me 3x minus 5 over x minus 3 minus 1 is less than or equal to 0. Now, all the rules about asymptotes, intercepts, graphing, etc. for rational functions or for rational functions with one numerator and one denominator and nothing being added or subtracted behind them. So in order for us to continue, we need to combine these two things. This is like minus 1 over 1. In order to subtract fractions, what would I need? A common denominator. So this one has a denominator of x minus 3. I'm going to give this guy a denominator of x minus 3, which means I have to multiply the numerator of x minus 3. So this is 3x minus 5 over x minus 3 minus x minus 3 over x minus 3. Which really just to me says minus 1. So you got to get common denominators, give that 1 the factor that is missing in the denominator. But you got to give it to the numerator and the denominator. Okay, now that I have common denominators, I can keep the common denominator x minus 3. I can combine like terms in the numerator, but be really careful here with this minus sign, right? I'm subtracting x and I'm subtracting negative 3. So that's going to turn into plus a negative x and a positive 3. I always just distribute my sign so I avoid mistakes. And that gets me 2x minus 2 for my numerator. Okay. But now I've combined it, so instead of having two things that are being subtracted, I have one rational function. And now I can answer the questions about critical points. So you guys told me the critical points were the x-intercepts and the vertical asymptotes. So for x-intercept, I can set my numerator equal to 0, 2x minus 2 equals 0, x equals 1. That's a critical point. For a vertical asymptote, set my denominator equal to 0, so x equals 3. So I have two critical values for the rational functions, 1 and 3. I've got one x-intercept, I've got one vertical asymptote. Now I'm going to make that number line where I test the intervals. I do usually try to mark on my number line, like, okay, the x-intercept was 1. So that's when the function equals 0. The 3 was my vertical asymptote, so this is going to be undefined. So whatever happens at 3, if that's part of an interval, it needs to be in parentheses. I'll have to decide if 0 gets included or not. Okay, now I'm going to test. So in the middle, I might test 2. This time I really only have to test like my numerator and my denominator, and I'm just going to do signs again. So 2 times 2 minus 2 is positive, and 2 minus 3 is negative. A positive divided by negative is a negative. Maybe I'll test 0. Well, that's going to be negative over a negative, which is positive. And then over here, I can test, I'll just pick 10. That's positive over positive. Pretty quick for me to see that. So then this section is positive. And now I answer the question. Less than or equal to 0. So I'm looking for negative parts. I only got one, right? My values are going to be 1 and 3. And now I have to decide. Brackets, parentheses. For 1, if that's the x-intercept, bracket. It could be 0. For 3, parentheses. That's undefined. There's nothing happening there. And then my number line answer or you could do closed on the left, open on the right. Okay, any questions about what we did right there?